In this lecture, we are going to see the topic that is related to the analysis of proper cantilever beam subjected to a central point load. Coming to the problem statement, determine the reaction components for the proper cantilever beam subjected to a central point load as shown in figure. Draw shear force and bending moment diagrams. So coming to the picture, so here AB is a proper cantilever beam. It is subjected to a point load at the center and it is having a span length L. So this load has been dividing this AC segment and BC segment equally. So first we are going to determine the reaction components for this entire proper cantilever beam. So we'll check whether the number of static equilibrium conditions are sufficient or not. So for that, we are going to find the degree of static indeterminacy first. So before going to that, first we'll calculate the number of reactions for this proper cantilever beam. So as here the support A is a fixed support, you are having three reaction components. That is, one is horizontal reaction, another is vertical reaction, and another is moment at A. And next, at coming to the B support, as it is a roller support, you are having only a vertical reaction, that is RB. So therefore, the total number of reactions here are 4: HA, RA, MA, and RB. Now coming to the next step, we are going to see a number of static equilibrium equations. Those are three. That is summation in x direction forces and summation in the y direction forces, and then moment in that plane will be equal to 0. So there are three static equilibrium conditions. Now coming to the degree of static indeterminacy, it is number of reactions minus number of static equilibrium equations. So therefore it is 4 minus 3, it is 1. We'll balance the forces now. So we'll take sigma fx equal to 0. So as you can see in this picture, there is no inclined load or there is no externally applied horizontal load. Therefore, HA will be equal to 0. Next is sigma Fy equal to 0. So that is summation of upward forces will be equal to summation of downward forces. So that is RA plus RB. So these are the reaction components at the supports, whereas W is your externally applied load. Therefore, we get RA plus RB will be equal to W. Next, now what I'm going to do is, we are going to divide this entire proper cantilever beam into two parts. That is, one part is a simple cantilever beam with a point load at the center. So here we are removing the prop here. So now making this structure to be a determinate structure. And next, second part is, we are taking the cantilever beam only with vertical reaction upward at the free end. So when we combine these two, you are going to get this proper cantilever beam. So we are going to analyze it individually. Then we are going to combine these two things. Then we are going to get the final proper cantilever beam. So now I am taking here the vertical reaction, whatever it is there. So the RB is taking as a redundant force. So RB, we are going to find it. So coming to the next slide. Here we are going to find the deflection at the free end for a cantilever beam that is subjected to a central point load. So I am taking a cantilever beam which is having a point load at the center, and now the deflection of this beam is like this. So the deflection curve will be like this. So at the fixed support, there is no deflection. So at free end, you are having a deflection delta B. So this delta B you are going to find out now. So to get this, what we are going to do is, you can see in this picture. So at the load acting, you are having a delta C, that is deflection at this C portion. Now what I am going to find is delta B. So this delta B will be equal to, you can see here, this delta C plus delta 1. So my aim is to find out now delta 1. To get this delta 1, what I am going to take is, I am going to take this triangular portion. So now tan theta c will be equal to this opposite side by adjacent side, that is delta 1 by L by 2. So tan theta c is delta 1 by L by 2. So here I am considering delta 1 will be equal to L by 2 into tan theta c. So as the slope here, the angle is small, we are considering. Therefore, tan theta c is approximately equal to theta c. Therefore, we are getting delta 1 will be equal to this L by 2 into theta c. So after getting this delta 1, what I am going to do is, I am going to substitute in place of delta 1, theta c into L by 2. So after getting this equation, we are going to find delta c and theta c. So here this is a delta c and here it is a theta c. So delta is nothing but the deflection at this point and theta is nothing but the slope at this point. So as we know that, so already we have learned in the previous deflection of beams. So for a cantilever beam, when it is having a load at the free support, so when we take this distance as A, so this is a deflection curve. So for this, delta at this point will be equal to WA cube by 3EI. And whereas theta slope is nothing but WA square by 2EI. So this is the things we have derived in the previous courses, deflection of beams. So delta is nothing but WA cube by 3EI. Therefore, it is here A is nothing but L by 2. So when you substitute here, you are getting this value, that is WL cube by 24EI. Similar way, theta c is nothing but WA square by 2EI. So that is W into L by 2, A is L by 2. When you substitute this, you are getting WL square by 80I. So after getting these two, when we add in this delta B, that is delta C plus delta 1. So here delta 1 is nothing but that theta C into L by 2. So after substituting all these values, we are getting this delta B will be equal to 5WL cube by 48EI. So this is a final delta B we are getting 5WL power 4 by, sorry, L cube by 48 EI. This is a deflection at this free end when you are having a point load at the center. So I'm directly using this formula, that is 5WL cube by 48 EI. So coming to the next slide, you are going to calculate the reactions here. So balancing the deflection at this point. So this is a question we have. So for this proper cantilever beam, you can see that the net deflection at this B is 0. So this is a consistency condition I am taking. So as we divided this entire proper cantilever beam into two parts, one part is cantilever beam with the point load and another part is cantilever beam with the vertical reaction. So here you can see, due to the given loading, that is central point loading. So for this cantilever beam, so we are having a deflection in downward direction as the load is acting downward. So the delta here we are getting it as 5WL cube by 48 EI. So this one already we have seen in the previous slide. So this is L by 2 and this is L by 2. This is C. So this is a deflection part and this is a downward deflection. So now the downward deflection is given by this formula. Now coming to the next segment, that is you are having a second part, that is a cantilever beam which is having a upward reaction at this B support. Therefore, you are having a upward deflection. So this upward deflection formula is RB into L cube by 3AI. So as we know that the net deflection at this B support is 0. So summation of these two will be equal to 0. So that means one is downward deflection, another is upward deflection. Therefore, both are equal. So in the next step, from the consistency condition, we can say that the net deflection at end is 0. Therefore, this 5WL cube by 48EI will be equal to RB into L cube by 3EI. So now we'll get RB value as 5W by 16. As we already know another equation, that is sigma Fy equal to 0. That is RA plus RB is W we know. So from this equation we got RA value as 11W by 16. So this is how we calculated the reactions RA and RB. So just the net deflection at B, we have taken it as 0. As there is no settlement in this support and all, so we are considering it as a rigid support. So as we equated the deflections, upward deflection to downward deflection. So after equating it, we are getting the RB value. Then by using this equation, that is sigma Fy equal to 0, we got the RA value. So after calculating these reactions, next we are going to calculate the momentum. So for calculating the moment, I am considering the RA and RB values here. Then moment at, here it is not A, moment at B is equal to 0. So that means RA into L minus this W into L by 2 minus MA will be equal to 0. So here you can just see this RA is in clockwise direction, so it is positive. This W into L by 2 is in anti-clockwise direction, therefore it is negative. And this moment is in again anti-clockwise direction, therefore it is negative about this B point. So by substituting RA and RA here, so finally we got MA value to be 3WL by 16. So as we are getting this value to be a positive value, whatever the sign we are assuming for MA, so this is correct. So it is in the anti-clockwise direction only. For suppose if you get this MA to be a negative value, then you have to change this anti-clockwise moment to be a clockwise momentum. So this is how we are going to calculate the momentum. So next, after calculating the moment, our next step is to draw the shear force diagram. So before drawing the shear force diagram, let us consider all these reactions RA, RB and MA. After writing this, we have taken the beam, propped cantilever beam. So for this propped cantilever beam, I just took a section XX in the BC segment, which is at a distance of X from the B support. So at this B support, we can see X is equal to 0. Why? Because here B is considering as an origin here. So as we are starting from the B, here X will be equal to 0. And at A, X is equal to L. So here we have to cut the section in two times. So one segment is in BC section, another is in AC section. So first we consider the section to be in BC. So this is a sign convention. So sign convention for the shear force. So sign convention here is, you can just consider when we take any element here, any segment of the beam here. So when we cut a section in this beam, so towards left hand side, or towards right hand side, when the arrow is making like a clockwise in direction, so then that direction is said to be a positive shear. And again in next case, you can see the negative shear. So coming to the negative shear, towards the section, when you are considering the arrow to be is in the anti-clockwise direction, so then this shear is to be considered as negative shear. So this is how we are going to take the sign convention. Now when we write the shear force at this XX section, so here this RB reaction is in the anti-clockwise direction, therefore it is minus RB. So we can write shear force at X section will be equal to minus RB. So that minus RB is nothing but RB is 5W by 16. Therefore, it is minus 5W by 16. So this limit is from only X is equal to 0 to X is equal to L by 2. So this distance here is L by 2. Up to this limit. So again, I am considering the section in AC segment. So when we consider a section in AC segment, you can consider like this. So which is having a x distance from B to this section. So this is an x distance. So when we write the shear force equation, so here at B, you're having again an anti-clockwise direction. So that is minus RB. And here again, you're having a load of W, which is in clockwise direction. So it is plus W. So the limit here is from x is equal to L by 2 to x is equal to L. So this is L by 2 to L. So when we solve this shear force one, you are getting 11W by 16. So from 0 to L by 2, it is negative value of 5W by 16. And from L by 2 to L, it is a positive value of 11W by 16. So after getting these values, you can just see 0 to L by 2 minus 5W by 16, and L by 2 to L, it is 11W by 16. So we are going to have a downward value of from x is equal to 0 to L by 2, it is 5W by 16 negative, and from C to A, you are having a positive value of 11W by 16. So this is a shear force diagram. So at C, that is L by 2, it is changing from negative to positive, the shear force. So this is how we are going to draw the shear force diagram. Now coming to the next segment, that is a bending moment diagram. So same, we have considered the beam, so which is having AB support, and this is x is equal to 0 and x is equal to L. So these are the reactions what we found in the previous slide. So this is your RB. So RB is 5W by 16. And when we took a section between this BC segment, so this is XX section, which is having a x distance from this B. So now coming to the sign convention. So when we cut a section at any point on the beam, so when the arrow is heading toward upwards, so one direction can be clockwise and another direction can be anti-clockwise. But when the arrow is heading towards upwards, then we consider the sign convention to be a positive. And this positive moment can also be called as a sagging moment. So again, in the same case, when we cut a section, and when the arrows are heading toward downwards, then the moment we are going to consider it to be a negative moment. So this one we'll call it as a hogging moment. So here also, one side you are having a clockwise moment, and towards the other side you are getting a anti-clockwise moment. So this is the sign convention we are going to adopt for the bending moment. So now when we cut a section in this BC segment, and when we write a equation here, so bending moment equation will be, so this is upward towards the section, the arrow is heading towards upward. So it is plus RB into X. And the limits here are 0 to L by 2. So when I substitute bending moment at X is equal to 0, you are getting a 0 moment. And when we substitute x is equal to L by 2, you are getting the moment to be 5WL by 32. That is at the C portion. So this is a 0 moment at B, and at C you are having a positive moment of 5WL by 32. This is when the section is in the BC segment. Now again, in the same way, when we have the section in the AC segment, so this is an AC segment. When we have a section here, same sign convention. So when we write it, so this is RB into X, again positive value. The arrow is heading upward. And this B at C portion, when we consider, the load is acting in the downward direction, and the arrow is heading downwards. So the load into the distance we are going to consider. So this distance we are going to consider. So this distance will be W into X minus L by 2. So this is negative. So RB into X minus W into X minus L by 2. So the limit here we are going to consider is L by 2 is less than or equal to L, X is less than or equal to L. So when we substitute x is equal to L by 2, we are getting 5WL by 32. And when x is equal to L, we are considering, we are getting a negative moment of 3WL by 16. So that means 0 to L by 2, you are having at L by 2 a positive moment. Again at x is equal to L, we are having a negative moment. That means somewhere around in this C to A, it is getting a zero moment. So how to find this zero moment? So that one we'll call it as a point of contraflexure also. So we are equating this bending moment x equation to be 0. So when we equate this to be 0, we got x is equal to 8L by 16. So therefore at x is equal to 8L by, 8L by 11, it is not 16. At x is equal to 8L by 11, we are getting the bending moment to be 0. So this is how we are going to find. So after getting all these values, in the next slide, we are going to draw the bending moment diagram. So this is a picture that has been given, and these are the moments. At B, you are getting 0. At C, you are getting a positive moment. At A, you are getting a negative moment. So while drawing, first I am drawing AB, and this is the C portion. And at B, we have a 0 moment. At C, we are having a 5WL by 32. It is a positive moment, and it is at a distance of L by 2. And again, at A, you are having a negative moment, that is 3WL by 16. And so from B0 to C, it is a positive, and again at A, you are getting a negative. So at some portion, you are getting the moment to be 0. So that is at x is equal to 8L by 11. So this is how you are going to draw your bending moment diagram. That's all. These are the textbooks and references. Thank you.